All right, our next group of students is from the chemistry department. This is Dr. Harris's group.
Hi, I'm Talia Selembo, and this is Sara, Faucett, and today we're going to talk about the research we did this semester with Dr. Harris, which is the intermolecular hydroamination of allenes using a zinc catalyst.
So hydroamination is the addition of a nitrogen-hydrogen bond across a carbon-carbon multiple bond, like an alkene, alkyne, or an alene. And the alkyne is seen in the first reaction, and the alene is seen in the second reaction.
Hydroamination can be intermolecular or intramolecular, which we'll talk more about later, and it's an economical method for carbon-nitrogen bond formation because there are 0 byproducts in this reaction.
And then it can also be used to cyclize amino alkenes with unactivated terminal alkenes to produce pyrrolidines and piperidines. So amines are used in the pharmaceutical industry and the agrochemical, cosmetic, and industrial processes.
Amide groups are found in a lot of common drugs, such as acetaminophen, dacarbazine, and naphthalene. Acetaminophen is commonly known as Tylenol, and it is an over-the-counter pain reliever. Dacarbazine is used to treat different types of skin cancer, like melanoma, by decreasing the blood cell count in bone marrow. And naphthalene is an antifungal drug that can be used for athlete's foot and ringworm.
Because of the vast range of applications for nitrogen-containing compounds, development of new methods for the formation of carbon-nitrogen bonds are of great importance.
So there has been previous work done in intermolecular hydroamination of allenes using late transition metals as shown in the first reaction, as well as intramolecular hydroamination of alkenes using a zinc catalyst. And our goal is to see if we can do intermolecular hydroamination of allenes using a zinc catalyst. And the reason we want to use zinc is because it is redox inert, which means it has a longer catalyst lifetime and higher functional group tolerance than other late transition metals, which eliminates issues with air and moisture sensitivity.
Zinc is also less expensive and less toxic than other late transition metals like gold and rhodium. For example, 125 grams of zinc is only $76, while 250 milligrams of rhodium is $451, and this is from the TCI laboratory website. And zinc also produces less waste and less chemical byproducts than the late transition metals that have been used for hydroamination.
Using a zinc catalyst may also enable a new way to synthesize chiral amines from axially chiral allenes. And this is because there's no evidence of zinc racemizing chiral allenes, but there is evidence of gold complexes racemizing chiral allenes.
So here's some of the equipment that we use during our research, and we'll talk about it today. The rotovap is used to reduce pressure, which lowers the boiling point of the solvent and makes it easier to boil the solvent out. A schlinkline is used for materials that are sensitive to water or air by keeping them in a controlled nitrogenous environment. And a flash chromatography column is used to separate and purify compounds by polarity. So we both started with the same compound, tropolone, and added a tosyl group by mixing tropolone and tosyl chloride and pyridine, and then stirred them for approximately 24 hours. We then filtered and rinsed the solids with ice-cold water and recrystallized with hot ethanol. We allowed our products to cool and then vacuum filtered out the solids.
So for our next reaction, we used 2 different amines, isopropylamine and cyclohexylamine. To produce both products, the tosyl tropolone, which is product 2, was placed in an ice bath. And then isopropylamine was added to create product 3A, and cyclohexylamine was added to create product 3B. The flask was wrapped in foil and left overnight to stir and come to room temperature.
And then the workup for both reactions was the same. The contents were vacuumed under reduced pressure and then taken up with 2 molar sodium hydroxide, then extracted twice with 2 milliliters of DCM. The organic layer was then rinsed with brine and combined. The combined organic layers were dried with magnesium sulfate, and the contents were transferred to a vial and again vacuumed under reduced pressure to evaporate any DCM. The sample was purified using a chromatography column, and then a mass spec was taken.
So these are the mass spec results for product 3A, which contained the isopropylamine compound. There's only one peak in the chromatogram, which is the first one shown, which indicates that our sample was well purified. And the mass spec, which is the second, shows the molecular ion peak and base peak are the same at 163.1 grams per mole. And the molecular ion peak is also the same molecular weight as my compound, indicating that we reached the desired product.
And these are the mass spec results for product 3B containing cyclohexylamine. The chromatogram shows one major peak. However, there is a second peak barely visible at about 8.5 minutes. This slight impurity was small enough so that we moved on with this sample. And the molecular ion peak and base peak are the same in the mass spec at 203.1 grams per mole. So this is also the molecular weight of my compound, and it shows that we made the desired product.
For our second reaction, we followed the same steps, and isopropylamine was again added to 3A, and cyclohexylamine was added to 3B. We started by flame drying a round bottom flask with a septum and Claydon adapter attached, and the reason we flame dried it was to remove any extra moisture that could be in there. We then added trimethyloxonium tetrafluoroborate and placed it under nitrogen, which gave us the intermediate product that you see there. And using DCM, we dissolved the amine. Ooh, something happened. And using DCM, we dissolved the amine and trimethyloxonium tetrafluoroborate separately, and then added the amine to the round bottom flask to let the reaction stir for 3 hours. Then, leaving the reaction on nitrogen, we placed our flasks in an ice bath and let them cool overnight. Afterwards, we rotovapped compound 4A and added ethanol to recrystallize, and then it was vacuum filtered and left on the house back to dry out.
So compound 4B did not crystallize, so we rotovapped it to remove extra solvent, but we believe to purify the sample, we're going to have to do a flash chromatography column.
For our final synthesis step, which we have not gotten to yet, we want to make our zinc catalyst. So shown are our products 4A and 4B, which is what we have right now. And we want to add dimethyl zinc, which is pyrophoric, which means it will spontaneously catch fire in the presence of air. So we will need to use that Schlenk line to add the dimethyl zinc, which will then deprotonate the nitrogen and create that bidentate zinc molecule, which we can use as a catalyst.
We want to use the zinc catalyst to hydroaminate an alane. First, we'll need to synthesize the alane, which is seen in the top left. Then we would begin screening reaction conditions that would allow for intermolecular hydroamination of this alane. Possible acids we could use include triflic acid, ammonium salts, and possible solvents are THF, toluene, or DCM. The temperature cannot be higher than the boiling point of the solvent we're using, and in similar reactions, the temperature is usually 0 to 100 degrees Celsius. In order for this reaction to be practically feasible, our goal is for the reaction time to be less than 48 hours.
So we would like to thank Dr. Harris for being our research advisor and Mrs. Cooper and Wofford College for supplying materials and funding.
And then we would also like to thank our group members, Ethan de Blasio and Jones Alexander.
Any questions for this group?
Sorry, I think you already said it, but what was DCM?
So it's a solvent that we use, and it stands for dichloromethane.
Other questions? All right, thank you.